So here we're gonna be looking at the infrared spectroscopy. All right. Now infrared. Now we're just looking at another area of light. We've looked at UV vis already. Now to look at the infrared spectrum. Now the origins of absorbance. Now absorbance is kind of weird as it relates to this, right? Because we're not gonna really be seeing any type of transitions really. Now, the energy level of infrared light corresponds to the energy required to cause molecular vibrations, right? So we're not going to really have any complete absorbance and emittance, but the molecules absorb just enough energy to result in these type of molecular vibrations. So we're not going to have color being emitted, but molecules are going to be moving, all right? So each frequency of light has a certain energy. Energies in infrared radiation corresponds to the energies involved in bond vibrations. Infrared spectroscopy is the analysis of infrared light interacting with these molecules that will create these bond vibrations, right? It is used by chemists to determine the functional groups in molecules generally. So infrared spectroscopy measures the vibrations on the atoms, right, or atoms, and based on this, it could possibly determine the functional groups. I'm going to see what's happening here, right? Now there are different types of molecular or bond vibrations rather, and they really absorb, right? These different types of bond vibrations absorb at different types of frequencies. But we're not gonna look so much at the types of frequencies, but we have to look at the different types of ways in which the molecules can actually vibrate. And we're gonna be looking at CH2 group, right? The CH2 group are molecules like water, right, which can vibrate in 6 different ways. We're going to be looking at different ways the molecules can vibrate. So it can be symmetric, symmetric and asymmetric stretching, can be scissoring, rocking, wagging, or twisting, right? So here is symmetric stretching, when the two atoms, right, or when the two attached atoms move away and towards the central atom at the same time. So it goes out like that. You have antisymmetric stretching, right? When the two attached atoms don't move away and towards the central atom at the same time, so it is asymmetric. You also have scissoring, in which, as its name suggests, the two atoms move towards each other, right? And move away from each other, right? In that scissoring motion. We have rocking, in which we have it's like a pendulum, right? Swinging back and forth, right? With two of them. We also have wagging, in which it basically moves back and forth into the plane of the page or into the plane of the screen and out towards you. And we have twisting. It's like asymmetric wagging, in which they do the same thing but at intervals coming towards you. All right. So those are different types of molecular vibrations that we look at. So active versus inactive. How do we know whether or not something is IR active, right? How can we tell? IR only causes a vibration if there's a change in dipole during vibration. Therefore, these molecules need to be more or less polar. Symmetric bonds are therefore inactive. So something like like ethane right here, those are more or less inactive. Not much is going to be happening. The carbon-carbon bond in ethane will not observe an IR stretch. So an IR active bond is therefore a bond that changes dipole during the vibration. So if it already has a dipole, if it already is polar, and when we bend and stretch, it changes the dipole even slightly, it will be IR active, right? So we can note these vibrations with specific wave numbers, right? You're gonna get the wave numbers from the data specifically, right? This information should be on a booklet provided to you in your examinations, right? So you have to now really look at the different types of vibrations that different functional groups can give you and different wave numbers, right? And we have to also know whether or not they're strong, medium, weak, or broad peaks that you're going to be looking at within your graphs, right? So for example, an alkane would have a CH bond stretch at around 2950 to 2800, and this is a strong vibration, right? So you have to note these different things in order to be able to read the graphs, and reading the graphs come with practice. You need to practice them, right? So let's look at interpreting, right? This is a look at a graph of propanoic acid, right, in chloroform, right? So here we're gonna have different peaks. This is the graph. These are examples of graphs, right, that are derived from these different molecular vibrations. So at around this area, right, you're gonna have a very strong peak, right, at around 1715, right, and let's see if that corresponds to something. Let's look at the carboxylic acid, this group here, the carbonyl group here, from 1730 to 1700, right? This 1715 strong peak here is going to be well resembling the peak that our carbonyl group is supposed to be giving, right? And our OH group, this is a carboxylic acid. So let's look at the OH within a carboxylic acid group from 3400 to 2500, right? We're gonna have that large peak from in this general area, so it does correspond to the OH stretch, right? And it tends to be a broad stretch, so you have a broad stretch here, right? So IR can actually help us to determine the different types of functional groups present within the compounds, right? And it can also tell us the different types of R groups, different R groups that are present, right? So our general carbon hydrogen groups. Okay, so this is an example of 1, 2, 3, 4 propan. Oh, this is butanol here, right? So looking at the graph of butanol, this is a clear OH group around this general area, right? And then we're gonna have a high peaks in this area, showing that majority of the rest of the molecule are alkaline in nature. Not alkaline. What am I saying? Alkaline. It would be acelanate. Well, it would be alkenyl in nature, right? Alkenyl, right? So it's gonna be alkenes, R groups, varying R groups in this area, right? So this is how the graph looks for this, right? So you can pause and actually look at the tables, right, and see if you can identify your functional groups, right? This is an example here of this amine here, right? We're gonna have the different types of dips. So this dip here should be resembling our amine, right? So if we go back here in our amines, right, we're gonna have an NH stretch, right? In the 3500 to 3300, 3500 to 3300 here, this entire stretch is the amine. So you just need to relate them and be able to really identify the different peaks present on these different graphs. All right. So the fingerprint region now. So the so-called fingerprint region is below 1500 per centimeter, that wave number there. Vibrations in this region are often complex and hard to assign to a specific functional group of a molecule. So a given molecule, though, has a distinct pattern in this region, right? The reason for this region being called fingerprint region. So it has a very distinct pattern. So this fingerprint region here is very distinct to this molecule and this molecule alone, as well as this fingerprint region here, very distinct to our butanol, right? This region here is very distinct to our proanoic acid. So this is what we call our fingerprint region. That is usually really difficult to decipher, but it's only present in one type of molecule or one molecule itself, right? So if you differ it and let's say that we have butanoic acid, then the fingerprint region will change and be only specific to butanoic acid. All right, so that's what the fingerprint region is really about. Now, you guys need to be present, well, not present, but able rather to actually prepare the different samples for IR analysis. So for liquid samples, right, liquid samples can be sandwiched between two plates of high purity salts. Why salts? It is because salts don't have covalent bonds and they cannot be IR active. So we're going to use ionic compounds as our plates because they are not IR active. So these plates now are transparent to the infrared light and will not introduce any lines onto the spectra. They are not IR active, so they're safe to be used as containers for our liquid samples, right? Our solid samples now, there are two paths. You can either crush the sample with a mulling agent. We usually use the chemical Nugol, right, in a marble mortar and pestle, right? So we basically mull it down. We mortar and pestle, we crush it into this paste, right? And then a thin film of mull is applied onto the salt plates and then put into the IR spec machine, right? The IR spectrometer. So the mull is the paste that comes out of you grinding the sample, right? For sample 2 now, we can grind the quantity of the sample with a specifically high salt. So we can grind it with potassium bromide, usually used, right, to remove scattering effects of large crystals, right? So we generally grind it, right, because even though, right, these substances, right, tend to not really be IR effective, right? The large crystals can actually result in the bending of light and stuff like that, right? The refraction of light, etc. Right? So we tend to grind it down really, really finely to prevent any type of scattering effects from large crystals. And then this powder mixture is then crushed into a mechanical die press. So it's squeezed and pressed into a small pellet. And this pellet is now what is placed, this translucent pellet is now what is placed, right, in the path of the beam, right, to really be detected by IR, right? So here are two YouTube videos. I'll try to put them into this description. Right, these two YouTube videos are really good, right, to show you how these are really done. Right, so it's important that you know how to do this in case questions are asked: how to prepare a solid sample, or how do you prepare a liquid sample for IR spec. All right. Now the applications now infrared spectroscopy, specifically known as Fourier transformation infrared spectroscopy, right? FTIR is a powerful analytical technique used to detect the quantity or detect and quantify rather air pollutants. So we know that majority of the different molecules within the air, right, and our chlorofluorocarbons and etc., those things that contribute to climate change, global warming, right, actually are IR active. So we can determine the concentration of these different types of air pollutants in the atmosphere using IR spec, right? So this is how we're able to figure out, okay, there's this much amount of this substance in the atmosphere contributing to different types of global warming, right? And if these molecules are also IR sensitive, when infrared light comes from the sun, they tend to absorb this light and trap this light within the atmosphere, right? Within the Earth's atmosphere, and actually results in the heating, right, of the Earth. We spoke about in the introduction to spectroscopy and UV spec video the fact that IR light is really hot. It really heats up things quickly. So when these molecules are in high concentrations in the atmosphere, it can contribute to global warming and hence climate change, right? And we tend to use IR spec to figure out the concentration of these different types of air pollutants, right, within the atmosphere. Now, the limitations of IR are really, really apparent, right? To determine the structure of an unknown compound, IR spectroscopy can only determine the functional groups present. In order to fully elucidate the structure, other techniques are required, such as mass spectrometry. So we looked at UV, then we looked at IR, right? And now we have to know that in order to figure out the actual exact structure, we have to look at mass spectrometry. So that is it.